Thanks, everyone. Thanks for the intro and for coming to my talk right here immediately after lunch. We at Blue Data have been doing Hadoop and big data virtualization for quite a while now, and in the last year or so we've ported the Spark runtime to run within Docker containers, and that's what I'll be talking about this afternoon. I hope. Okay, so first of all, I'll just go through an outline of what we'll be talking about. First of all, I want to give some rationale about why we did this at all. I mean, Docker runs perfectly well on physical boxes. Why would you want to run it in a Docker container? Talk a little bit about the lessons that we learned in terms of networking, storage, CPU resource utilization. Give some information about the performance that we found out. Then hopefully the demo will work and I can show you a demonstration of what we did. And finally, we'll have some Q&A at the end. First off, when you consider Spark within the enterprise, it's slightly different than when you're considering Spark with a single data scientist working somewhere. The data scientist typically has knowledge of both the data science software, such as Spark or Jupyter or Zeppelin or whatever MapReduce they're using. And they also have a fair amount of IT knowledge as well in order to install new packages, build software, construct the Linux system, and so forth. However, in the enterprise, those are two distinctly different roles. The data scientist wants to have flexibility. They want the ability to run the version of Spark that they want and the applications that they want and access the data they want. And they want to do it in a timely fashion. And those needs are balanced against the needs of the IT organization for that enterprise, which is all about security, data security and network isolation, multi-tenancy, which means some data scientists can see some data scientists can see other data, and it's supposed to be controlled that way. So any solution that we came up with had to address these two needs. So we took a look at the existing Hadoop deployment models. There's two types. There's obviously on-prem, and then there is Spark as a service, or typically in the public cloud. But on-prem, there are actually a number of different ways to deploy Spark. First of all, it can be deployed as part of a distribution. So if you have a Hortonworks or a Cloudera distribution, you can install that software and then use Embari or Cloudera Manager to install and configure the Spark service running on top of Yarn. Alternatively, you can just download the Spark source itself from the Apache website, compile it, and install it on your collection of bare metal servers. Now, yesterday, I think in 2.0, it was announced that Spark with Mesos, so it's using the Mesos scheduler now. That's also a way of deploying your Spark services within your data center operating system. And finally, there's a way that we approached, which is you treat your Docker containers more or less as virtual machines, and you install your Spark services within those containers and assemble them into a collection of containers across hosts for a network. Alternatively, you can look at that looking like the Databricks Spark as a service in the cloud, or you can run your Spark cluster on the standard public cloud services such as Amazon, Google, or Microsoft. So what's the advantage of running Spark in a Docker container? Well, it's the typical advantages you get with running or virtualizing any application. You get automation, you get better use of your available hardware by being able to over-provision CPU. You get isolation, fault isolation, and then the flexibility and scalability to easily add or subtract resources from your Docker container, and in this case, the Docker container running Spark. So those are the reasons why you'd want to move to a virtualized platform with Spark. The counteracting argument, though, is what about performance there? That's usually the trade-off that we experience. So today, Docker is a powerful mechanism for packaging services and deploying them rapidly. You can also use things like Kubernetes to take a pod of services and deploy them. However, Docker is typically used in most cases today for a microservices architecture, which means a single application or a single service is running within that container. Then all the resources devoted to that container are used solely by that service. And that's great for most applications. However, Spark can be a distributed application, and it's a number of services working in conjunction. So you may have not only the Spark master or the Spark worker. You might have on the Spark master the Juniper server or the Zeppelin server. You might have other services running at the same time in parallel. And you want to schedule those as a single unit. And you want to do that and still maintain the performance of the bare metal server. So that's what we did. Our design was such that we deployed the Spark clusters as Docker containers, spanning multiple physical hosts. That kind of goes without saying. And as I just said, the master can run with additional services, and the workers can run with additional services as they're spread out. So we automate this, this instantiation of the cluster, do the automatic configuration, and then we link them together into isolated networks, and I'll go into how we do some of that work. But one of the other key things, if you want to maintain the power of virtualization, is you want to, as much as possible, not put storage into the virtualized unit. So in this case, containers. You don't want to put too much storage in there. If you're running HDFS within that container cluster with some storage local, and you're running name nodes and data nodes, you tend to ingest a lot of state into that container, making it less flexible, less agile, and consuming more resources. So what we have done is to actually move all the data outside of the container cluster. We'll show how we did that, so that when the Spark cluster comes up, it can come up quickly, it can be destroyed and recreated quickly, and still have access to the same data, so without re-ingesting data into the HDFS file system or whatever file system the Spark cluster is using. Everyone wants to see what the Dockerfile looks like. This is the standard Dockerfile. In this case, we're using the 1.5.2 version of Spark. We add on Scala and Zeppelin services, and those last two lines are some scripting services that Epic or Blue Data has added, which in fact run the configuration information the first time this Docker image is instantiated into a container. And it has two different flavors. It'll have a master flavor and a worker flavor. So depending on some of the information that's passed in at cluster instantiation time, it will determine which it is, so which mode it should operate in, and then how many workers should be deployed for this cluster. So now it's great, you've given me the background. Let's just talk a little bit about lessons. What we found is that the concept of virtual cores is still a very strong and well understood concept. What's less well understood is this thing about CPU shares, which is what typically occurs when you're using a container within Linux. You're allocated a portion of shares. No one really knows what that means. So what we did in our solution is that we still enabled the data scientists to specify their resources in a virtual core unit, and then we in the back end would convert it to CPU shares. This was actually key because you want dynamic sharing of resources. So even if you have multiple Spark clusters running on the same hardware, if you're not running a job on one of those Spark clusters, you don't want its CPU cycles to be dedicated to that cluster and not be able to use by someone else. With CPU shares, that's an easy way to do that. You can move them back and forth, and when a cluster starts to run a job, well, then it'll get its CPU share percentage. Interestingly enough, we did not do the same thing with memory, so we don't support over-provisioning. What we found is that if you have a Spark cluster and it's running along and then you start to swap, your performance really goes to hell in the handbasket. So we didn't want to enable Spark to have over-provisioning with memory. Our image management is pretty much the Docker standard open source image repository, except as I showed in the Dockerfile, we add some additional scripting. One tip, though, is that these Docker files can get quite large, especially with all this Spark software in there. So make judicious use of the Docker squash command to save size. In regards to the network, we were actually using originally Docker version 0.8 and then moving up to Docker version 1.10. So as you know, there was a lot of plug-in capability added to the Docker framework in the version 1.10 and beyond. So we're taking advantage of that in our next release. But today, we added to the Docker 0.8 release, we added the concept of persistent IP addresses. Now, these are things which are available in other plugins to the Docker, but we wrote our own because we felt we wanted to control the DHCP and DNS services so that we could tightly control the IP address. And then when the Docker container was restarted, or the host crashed and came back up. We have an HA solution. If the host came back up and reinstantiated the containers, we wanted to make sure those IP addresses were constant, so they were persistent across the entire lifespan of the container, not just for a single boot. And the way we implemented that is, as you would expect, we used VXLAN tunnels between the physical hosts. We used an open vSwitch to create these tunnels or bridges, tagged each packet with a VLAN tag as it's coming out of the container, routed it down through the OVS switch and across. I have in the next slide, I'll show a graphic of how this is done, but it's a way that we could have each of the container clusters run in a completely isolated network. And that was key for the security needs of the enterprise, where one Epic container cluster has access to some data, one has access to different, and they can't mix. With storage, one of the key things that we noticed is that the /root partition, which is the primary storage that you associate with the container, has to be very carefully determined so that it'll work for many of your containers. The issue is if you're standing up 20 or 30 containers or more, 50 containers on a single host, all of them have the same root size. So you can't change that very easily unless you bring the containers down and back up. So you have to make sure that root capacity is set correctly when you're going forward. What we did as well is we did not use the loopback mount. So if you're typically using Docker containers, the most obvious way you attach storage into a Docker container is what's using a loopback mount point. So a file is created in the ext3 or ext4 file system on Linux. A loopback device is created on top, and then it's plugged into the container. That's good, it's very simple, but it's very slow. So what we did instead is we took the physical disks on the drive, created a volume group, sliced it up using the Linux volume manager, and then attached standard volumes, devices, block devices straight into the container, and we got a lot of performance back once we did that. We also experimented a bit with using what would be equivalent of RDMs in ESX or VMware parlance. What that means is you attach a device straight into the container. Now you can do that, and what you'd like to do is attach something like dev SDA or SDB, so a standard SCSI disk or a SATA drive that you want to attach straight in. However, dev SDA and dev SDB are symbolic links rather than regular nodes in the proc file system, and Docker Containers doesn't allow you to attach symbolic links as devices into the container. So you can go ahead and use the standard disk devices in the DM, so the device mapper directory, and those are real nodes, not symbolic links, but they always have the risk of, as the server reboots, the ordering, the PCI ordering can change, and so you might not be able to, the disk that you think you're mounting maybe actually be a different physical drive. So getting back a little bit to the Spark network architecture that we used, the green boxes here indicate physical servers. There are two different Spark clusters, one red, one blue. The red one is spanning two physical servers, the blue one is just off to the side. And so what I'm showing here is that a packet that's generated by the Spark master will be sent out onto the red virtual network. It'll be tagged with the VLAN tag by the OVS server, sent out for the physical NIC, and then across a VXLAN tunnel over to the other physical box where it is sent up through the NIC, physical NIC there, and then through the OVS routing, we'll detect what VLAN tag was associated with it, and then fan it out to the appropriate containers belonging to that virtual cluster. So that's how we protect security. And then speaking of security, there's actually quite a bit of, this is probably one of the biggest issues that we encounter when we deploy Docker containers with Spark or Hadoop at the enterprise, and that is these concerns about containers. So what we first did is we run the container in non-privileged mode. For those of you who aren't really familiar with that, you can run a container in two modes. One is privileged, one non-privileged. If it's privileged, it pretty much has root access to everything, so it has a lot of power. You don't want that on a typical enterprise system where the IT department is controlling the resources on that host. So we run them in non-privileged mode, and then we actually set a number of the capabilities that are provided by containers to do the various isolation, and this gives a list of what those conditions are. So now to speak a little bit about performance. So what we wanted to do is measure what was truly the container overhead in our effort. So we took 10 physical nodes. They have the information here. So 36 cores, 112 gig of RAM each. We installed Cloudera 543 on those physical boxes, configured it with Spark 1.4, 1.5, 1.6. We tried a bunch of them. And then we ran the HiBench TerraSort benchmark across that 10-node cluster, physical node cluster, with three different capacity sets, 100 gig up to 1 terabyte. And we measured that performance. Then we did the exact same thing with containers. So we reinstalled Linux on those bare metal machines. We installed the Epic software, which is a collection of services that manages the containers. We then installed the container software itself and instantiated a 10-node cluster, or Cloudera 543 cluster running Yarn, with one container per physical box, okay, containing all the resources for that physical box. We wanted to see what kind of performance penalty there would be due to that overhead. What we found, there was actually very little penalty. So what you're seeing here is this graph. So there's, maybe with two or three, maybe up to 5% variation. You'll notice that the containers on Blue Data actually were a little bit faster than the bare metal solution. You wonder how is that possible? Well, one of Epic's solutions also is a read-ahead cache, and so it distorts a little bit of the performance, but that's the topic for another presentation. But so what I wanted to show here, and this is what we have borne out in the industry, is that it's pretty comparable. There's not a lot of overhead being added by the use of containers. Okay, what I'm going to try to do now is bring up a demo so that I can show you Epic in action. Let's see if I can connect to the network here. It dropped earlier, so let's see if I can. If not, I have a canned presentation, but I'd rather not use that one if I didn't have to. Let's see if it worked. No, I was afraid of that. Okay, so I'll have to go ahead and use the canned demo here. Okay. Okay, so this is let me just back that up. This first page is just a login page. It has nothing to do with the demo. It's just showing how Epic logs in. But what I want to show you is when we go to, it's not showing? Okay. Let's see. Thanks. Not yet? Let's see. Okay. Now it's showing. Okay, so what I wanted to show is, let's bring this back up. You log into the Epic system with the standard login solution. Then this is the collection of images which are in the library. These are standard shipped with Epic, but obviously they contain a number of Spark distributions, 161, 152, but you can add whatever you want. So it's trivial to go ahead and take the Dockerfile, modify it, add your additional software, and add it to the repository. But what I wanted to show is now you would log in as a regular user, and then click on the cluster instantiation page and create a brand new cluster. So this is all it would take, is you specify a name, select the type of cluster you want to create, the distribution of Spark in this case, and then finally give it a number of resources, and then submit the job. So that's it. That's the entire amount of effort it took to create a Spark cluster. So 5 or 6 clicks, and then within a minute, most of that time is not the creation of the container itself, but rather the configuration of the software, Spark software, after the containers have been instantiated. And what I want to do now is show you inside. So what these look like, this is a Spark container or Spark cluster running on Epic. In this case, there's 4 containers. Those containers are distributed across, I don't know how many, maybe 4 or 5 physical boxes, and these are the URIs that you would typically use to access that cluster. You'd access it just like you would a physical box. And so we can click on any of the process list ones here. So if you want to run the master or the observer, this is the standard, everything you'd normally see in a Spark master about running jobs and resources. If you want to bring up the Juniper UI, you can run a job here, and this will be submitted against the cluster running in the containers. This is just going through here. I just want to now move forward a little bit into, so using just a notebook. So you can now, this is logging into the server itself. You can use the curl command to actually submit jobs. And what we're running here is not just the Spark Plus cluster, but the Spark job server. So what we're showing is that we're submitting jobs directly to that. You use the URL as if it was a standard physical box. And then we'll go back and take a look at the Spark controller and see that those jobs were actually instantiated and submitted to this particular cluster. That's all I wanted to cover here. I apologize that the demo didn't work as well as I would have liked, but that's what we wanted to show, is that you can run Spark clusters quickly from containers, and you don't have a performance issue. So in order to wrap this up, I want to, and I know we have like a few minutes left, key takeaways is there is value in running Spark in a Docker container. Even if you're just doing it as a data scientist and you have a complete control of your machine, there is value in it. You get the best of both worlds. You get the security that IT wants from a physical environment, and you get the flexibility or the self-service environment you get from a public cloud, and performance is good. So if there's any questions, I'll take this now. I have a few minutes. I think it's 7 minutes left. And then if we run out of time, please come to the Blue Data booth afterwards in the expo, and I'll be happy to talk about anything there. Sir. Thank you, John. Thank you.
Those of you in the back, if you actually want to ask a question, can you please use these 2 mics in the front of the alley and line up? And I'll also have a mic running around, so we have somebody in the front.
Hi, thank you so much for the presentation. I was just curious, how is this different, say, from using like Kubernetes to do the orchestration? And second question is, one of the really benefits, I think, right, of running Spark clusters on using containers is that you can do this like resource Tetris, right, where then you can have other applications or services running at the same time.
Absolutely.
So I was curious. So one of the problems that I ran into was I can't have 2 Spark worker containers running on the same physical node because of local like port issues. Right. I was wondering if you guys like got around that.
Yeah.
Thank you so much.
Okay. Thank you. So there's a couple of questions there. First one is, why didn't we select Kubernetes or some other deployment opportunity? And we will. We're actually looking at Kubernetes right now. This product was in design and development about a year ago, and Kubernetes was not quite yet ready for enterprise use at that time. But there's absolutely no reason why we can't use its pod technology as a way of deploying the containers across physical hosts. Okay, so the second question I think was about shared resources. So if you're running other applications on the same host, is that it, or is it 2 containers on the same host?
Sorry, so the first one.
Okay, so and this is a product, and it's actually designed solely for running big data Hadoop applications. So it's not designed for anything else. But as we are going forward, and we see that the DCOS is becoming more and more popular in enterprises, we actually have it running with Mesos Resource Scheduler. So you can, in fact, run Epic, have the containers negotiate with the Mesos scheduler to get resources run, and then have those resources then released and used by another application later. So that is something that is coming in this. And then the final one is, yes, we do. The question was, I think, how do you get around the port issue? Well, each one of the containers has a different IP address. So I mean, those are completely different entities in the network. So you can have multiple containers accessing the same physical port on that box, using the networking that we put together.
Any other questions? Those of you in the back, if you want to answer the question, please line up in the mic.
So did I get correctly that all these containerized Spark clusters are using the same HDFS cluster? And isn't it causing like isolation problems?
Okay, so at least if I understand that. So you're asking, do all the clusters use the same HDFS file system? I did go into that in detail, but the answer is each of the clusters that comes up does in fact have a local HDFS, so it could store data locally. Best practices that we suggest, though, is that you don't use that. You only use that for some temporary data. But any true, your petabytes or terabytes worth of data would reside external to your cluster. And then we have a fast path as part of the value add that Epic has that allows the container to access remote storage using a different URI. Okay, and that's what we would suggest. So if you had 5 different Spark clusters on they would all be configured to use what we call data tap, which is a mechanism to reach external storage quickly, and then they could share the same HDFS file system in that fashion. Okay, and that can be Kerberos or non-Kerberos, so you can do whatever kind of protection or user access controls that you want to do on that solution. Okay.
Anybody else? Okay, give a big hand to Tom. Thank you very much.
Thank you.